All right, 21.2, going to expose you real quickly to a couple terms in nuclear chemistry that kind of run your daily lives. So, if you're labeling, 21.2 would be energy in nuclear reaction. So if we look at a chemical reaction, what we're going to have is there's a tremendous amount of energy stored in the nucleus of any atom. Remember, Einstein's famous equation E equals mc squared relates directly to the calculation of this energy. So even though the mass of an atom is incredibly small, the energy that we can convert it to is incredibly large. So if you look at the mass of one uranium atom, for example, it's only 0.0046 grams. Convert that to kilograms, you have 4.6 times 10 to the negative sixth. And then the speed of light is 3.0 times 10 to the positive eighth. You square that, and one atom of uranium, when it decays, can lose 4.1 times 10 to the negative 11th, or 4.1 times 10 to the positive 11th joules. That's a large amount of energy. So what happens if you take this energy and instead of doing one atom, it's a mole of atoms, or 1,000 grams, or a ton of uranium, or 10 tons of uranium. You can kind of see the energy that we can harness. And this energy is carried out in a reactor, and it's called nuclear fission. Fission, remember, is where the atoms are binding together, or breaking apart, excuse me. Fission is where they are breaking apart. So you can see here the chemical reaction. One neutron is going to hit an atom of uranium-235, and what's going to happen is it can break into a variety of things. You can see it's going to break into three things up here, Te, zirconium, and 2 neutrons, or barium, krypton, and 3 neutrons below. You're going to bombard an atom that's radioactive with a neutron to start the process. And what happens is more neutrons are produced, so it's a chain reaction. So nuclear fission continues to happen. The process is called a chain reaction because you create more neutrons, which bombard more things, so it's a nuclear chain reaction. If there are not enough radioactive nuclides, so you start running out of radioactive material, the chain reaction will die out. Therefore, the vocabulary word here real quick, the minimum amount of material for a chain reaction to be sustained is the critical mass. So all of a sudden, if the reaction is going to die out at 2 kilograms, maybe 3 kilograms, or 2.1 kilograms is your critical mass. That's the mass needed for that reaction to continue. This process is created when we have nuclear energy here in Minnesota and all over the world, such as in Red Wing or Monticello over the United States and 3 Mile Island. What happens is, though, nuclear reactors, since they produce so much energy, there's a large amount of heat that is generated by this reaction. That heat then produces steam that turns a turbine connected to a generator. That turbine is going to produce electricity. This reaction is kept in check by the use of control rods. These block the paths of some neutrons, keeping the system from reaching a dangerous supercritical mass. So these control rods go up and down, controlling the fuel. What happened, if you remember about probably 5-7 years ago in Japan, is that this cooling tank, which the entire thing is involved in, broke and was open to the environment, and radioactive material was seeping out into the environment and into the ocean. So fission is where we break them apart. Fusion would be a much superior method of generating power. And fusion is where we combine atoms together rather than break them apart. The problem is, to achieve fusion, we need to be at several million degrees Kelvin in the plasma-like state of a substance, which is practically impossible to achieve on planet Earth. But what's the one place that achieves this? The sun. And that is why the sun is so efficient at making millions of megawatts of energy per second, and at a rate that it's been doing for 4 billion years and will continue to do for 4 billion years. So fission is when we bombard a radioactive atom with a neutron and set off a chain reaction where it breaks apart into other atoms, and other atoms and more more neutrons to continue the reaction. Fission, that is fission. Fusion is where we combine atoms to make an atom, more of a higher up atom. So we combine two hydrogen atoms to form a helium atom. We're working on doing this. We're showing promise, but there's work to be done in the field of nuclear fusion as an sustainable energy source on planet Earth. Not any math, not anything along those lines, just exposing you to the types of vocabulary that you may come across when you're talking about nuclear chemistry. This will conclude section 21.2.